Okay, hi guys. This is Miss Davies. So we're doing just a little bit more with your forces notes today. So you have at the bottom of, the pages aren't numbered at this place. Okay. Newton's second law and dynamic forces. Okay, so this is where we talk a little about friction. So friction is anything that opposes motion. Okay. Friction, it's due to adhesion between surfaces, a rough surface, a deformed surface. So the rougher it is, the more friction you have. You can think of air resistance, drag, you can think of that as friction. Literally anything that opposes motion is considered friction. Okay? Static friction, this is when the object is stationary. So that means it's not moving. Okay? So that's like a wall. Like if you pushed and pushed and pushed on a wall all day long and it didn't move, that would be you pushing against static friction. If you're pushing against something really heavy, that just won't move because it's got too much friction. You're pushing against static friction. Okay? Now, at the moment something starts to move, you are overcoming the static friction. So the maximum static friction occurs immediately after an object starts to move. So we have something called a coefficient of friction. It's a Greek letter mu. Okay, so it's kind of just a weird little m. Mu s is the coefficient of static friction. So the s stands for static. Okay. The other type of friction that we're going to deal with is kinetic friction. Kinetic friction is when an object is moving. Okay. The mu k stands for kinetic. Okay. So kinetic literally means motion. So if something is moving against a surface that is rough, even a little bit rough, it has a little bit of kinetic friction. Okay. Static friction is always greater than kinetic friction. So mu s is always greater than mu k for a surface. Okay, so you have this equation. I think it's on your formula sheet. So friction is just equal to the coefficient of friction times the normal force. So you have to have a surface to have friction to calculate it this way. Okay. Moving on. Okay. So which experiences more friction, a push or a pull? So here we have a box and it has some mass, and in this instance it's being pulled. Sorry. And in this one it's being pushed. So this is FA, force applied. Okay? And this is at some angle theta. So for the pull, my force diagram, it has Fg, it has a surface underneath it, so it has Fn. It's being pulled up and to the right, so we have our vectors kind of up, so Ty, and to the right, Tx. Okay, so they're components, so I think we should probably start drawing our components with dotted lines rather than straight lines, okay, because they are components. And because it's on this surface, and they mentioned friction. There's friction. Friction opposes motion, so I'm assuming that if I'm pulling it this way, then it's going to slide that way horizontally, which means the friction is opposing, so it's going the other direction. Okay, so I know that with the pull, my net force in the y is Fg plus normal plus some tension in the y, and that's going to be 0 because it's not moving up and down. So that means my normal force is my gravity minus my tension in the y. Okay. For my pull, same mass, so it has some gravity. It's on a surface, so it's got some normal. It's being pushed down and to the right, so we're going to draw a vector component down for FAY and a vector component side for FAX, and then friction out the back. Okay, so for this one, my Fy is going to be my normal plus gravitational plus Fay, which equals 0. Now, my normal is going up, my other two vectors are going down. So in this case, my normal is equal to Fg plus that other component vector in magnitude, okay? So, what's happening is the normal force on the, this is a push, wow. Words are hard for me. We've already discussed that. Push, okay, sorry. So on the push, your normal force is going to be greater than your gravitational. On a pull, your normal force will be less than your gravitational. So your normal force is what determines your friction, right? Because remember that your friction equals the normal times the mu, okay? So the higher your normal, the more friction you have. So that means that the force on a pull is less than the force on a push, because normal force is less for a pull, so friction will be less. So it should be FF of a pull, FF of a push, friction. Okay. Okay. Cool, cool, cool. Okay, moving on. Atwood's machines. So these are kind of fun. So when you have an Atwood machine, and they can exist at different angles and stuff too, but this is just kind of a simple one. So simple Atwood machine, you have a pulley and a string, and it's hooked up to something, a mass on either end. And if you let the system go, it'll usually accelerate in one direction. Okay, so that's really all we're doing here. Sorry, my phone rang. All right. So we're just going to jump right in here. So I have in the image to the right, I have mass 1 is half a kilogram, and mass 2 is 0.25 kilograms. And the surface that this is on has a coefficient of kinetic friction of 0.3, and I want to know the acceleration of the system and tension in the rope. So if I were holding this, it wouldn't move, but when I let it go, which direction is it going to go? It's going to go, so this is going to go this direction, and this is going to go this direction, which means your acceleration will be in both of those directions, okay? So I know in order to do this, I'm going to first have to draw force diagrams, okay? So for M1, so it's a half a kilogram. I know it's got Fg. It's on a surface, so I know it's got normal. It's being pulled by a rope, so it has tension, and they told me that it has a mu, so it must have friction opposing the motion. Okay. And I'm assuming that I have more tension than friction. Okay. So that's all I have for that one. For the mass 2, there's nothing touching it in the horizontal. It only has vertical things, right? So it's going to have Fg and tension. and I'm assuming it's going to accelerate downwards, so my FG should be a little longer than my tension, okay? And this is 0.25 kilograms. Okay. Oh, I'm sorry, you can't see that, can you? There we go. Okay, so we're going to treat the system as a single object. Treat the system as a single object moving in a direction. Call that direction of motion positive. So that direction is positive, and even though we're saying this is going to go down, we're going to say that that's a positive direction, okay? We're going to write net force equations for each one. So for my M1, my net force in the X is equal to friction plus tension, and it's going to move and accelerate in that direction, so I'm going to call that MA, not 0. Okay? So, let's see, what else do I know? I can do my Y, so my Y component forces, it's going to be normal plus gravitational. So that equals 0, because it's not going up and down. So that means my Fn equals my Fg. Okay, so I can plug that in because I know Fg is mg. So 0.5 times 10 is 5 newtons. Okay, so my Fn is 5 newtons. I know that my mu k is 0.3. So I can find my friction. My friction is going to be 0.3 times the 5 newtons. And so that's going to be 1.5 newtons. So I know my friction, I don't know my tension, I know my mass, and I don't know my acceleration. So I can actually plug this and the mass into this equation and have something to use, okay? So I now know that 1.5 plus tension, oh wait, so my friction is going that way and my tension is going that way. So if I've decided this is the positive direction, then my friction is going in the negative direction, okay? So that means that's going to be negative 1.5, okay? Plus T, and that equals, the mass was 0.5, so 0.5 times A. Okay, so I'm done with M1. That's as far as I can get. So then I look at my M2. My M2 only has Y components. So my M2, my sum in the Y is tension plus gravitational, and that equals MA, because it's accelerating, okay? So, I don't know my tension, but I can find my FG, right? So I know that my FG equals mg, so that's 0.25 times 10, which is about 2.5 newtons. Okay, so now I can plug in information that I have for this. So in this one, my tension is going in the negative direction. So I'm going to think of that as negative tension, because up is negative, because this is going to go in this direction. So I'm saying that down, that direction is positive, that direction is positive. So the other direction is negative. Okay? Which means my tension is negative. Okay? Plus my gravitational, because that's going in the positive direction, so that's 2.5, equals 0.25 A. Alright, so what does it say now? It says combine the force equations corresponding to the motion of each object into a singular net force equation. Okay, so that means I'm going to add that equation and that equation together. Okay, so I'm going to have negative 1.5 plus t equals 0.5a. So I'm adding these together. So when I do that, negative t plus t goes away. 2.5 plus negative 1.5 is 1.0. 0.25 plus 0.5 is 0.75. So then I can just divide both sides by 0.75 to get my A. So then A equals 1.33 meters per second squared. So that's my acceleration. Okay? So I've solved for the acceleration of the system. Now I need the tension in the rope. Well, I have two equations that involve tension. I have this one, and I have this one. I'm going to do the one where its tension is positive, okay? So I'm going to plug it back into there. So now I'm going to plug this back in to here and find T. So negative 1.5 plus T equals 0.5 times 1.33. So I'm just going to add 1.5 to both sides. And that will give me my T. So T equals 2.17 newtons when you stick it in your calculator. Oops, there we go. Okay, cool, cool, cool. And I think that's all we had to do for today. Yep, next lesson is on inclines. So good luck with your homework. Bye-bye.